Right, okay, so we're going to go through the reactions of benzene, and we're going to go through 3 reactions. So we're going to go through the halogenation of benzene, the halogenation of benzene. We're going to go through alkylation, and also acylation, which is very similar. Acylation, which is commonly, both of those are commonly known as the Friedel-Crafts reaction. Friedel-Crafts reaction. And we're also going to go through the nitration of benzene. And you'll see how similar, sounds quite a lot, 3 reactions, but you'll see how similar they are. Okay, so the first one, the halogenation of benzene. Okay, halogenation of benzene. Halogenation, sorry, just take a moment to write it. Halogenation of benzene. So what you need to know is you need to know the chemical equation and the mechanism. Okay, so we're going to take benzene, which is a hexagon, a circle, C6H6, benzene. And we're going to, you can put bromine or chlorine, but we're going to react benzene with bromine. Okay, now before we go through this, we need to do a bit of revision first. So let's just do some revision first, and the revision is going through alkenes first. Okay, so making sure that you understand what happens with an alkene. Yeah, okay, so if you take a cyclohexene, yeah, plus bromine, okay, and this is bromine water, yeah, and remember that bromine is an orange, okay, orange color. Now do you remember what happens when you add bromine to an alkene? So the double bond breaks and bromine is added across the double bond, and you end up with where the double bond was, you'd end up with a Br and a Br, like that, and this chemical is called 1,2-dibromo cyclohexane. Cyclohexane. Yeah, okay. Do you remember the mechanism? The mechanism for this? So the you've got your cycloalkene, you've got your pi bond, yeah, and along comes the bromine molecule, okay, and the bromine molecule approaches the pi bond and becomes polarized. So the bromine molecule becomes polarized, yeah, which means that, remember the pi bond is a pair of electrons that are sticking out of the plane, and all the electrons in the bromine molecule run to the other end of the bromine, and you get a dipole, yeah, and it becomes polarized. And this is because it's a localized pi bond, yeah, localized pi bond. And then the pair of electrons from the pi bond attack the bromine. Remember what a curly arrow, shows a movement of a pair of electrons. Movement of a pair of electrons, we're just doing a bit of revision. Movement of a pair of electrons. And then the bond between in the bromine molecule breaks, and both electrons go onto the bromine, yeah. So this is just a bit of revision from the alkenes, of what happens with alkenes. Okay, and then there's your 6 carbons. So one of the carbons has now got a bromine, yeah, because this bond has formed. Movement of a pair of electrons to form or break a covalent bond. Both electrons, and this carbon is now 1 electron short. You can watch the video on alkenes if you want a bit more information. And the other bromine has got its electron back, and the other electron as well. It's got both electrons in the bond, yeah, both electrons. So it's got too many electrons, it's got a negative charge. And then here, that comes in and attacks the carbocation, and you get your product, which is the 1,2-dibromocyclohexane. Yeah? Can you remember that this is called an addition reaction? So why is it called an addition reaction? Because two items are adding together to make one item, and it is called electrophilic addition. Electrophilic addition. Squeeze it in there. Oh, electrophilic addition, because the bromine is acting as an electrophile. It'll be easy to go this one actually. The bromine is an electrophile. Do you remember the definition of electrophile? An electrophile is an electron pair acceptor. Okay, so it's important for you to remember that and understand that before you look at the reactions of benzene. So that's the reaction of an alkene of a pi bond. Yeah. So let's go back to benzene then. Right. So we're going to have a look at the mechanism. Look at the mechanism. Okay. So you have a sorry, get a pen color. So you have benzene. Okay, and you have the bromine molecule. Okay, benzene and the bromine molecule, right? So this is the mechanism now. We're just looking at the mechanism. Now, the benzene ring, okay, the benzene ring cannot polarize. So the benzene ring cannot polarize the bromine molecule, okay? And that is because the pi bond, the pi ring is delocalized. Yeah, so the pi ring, the pi electrons are delocalized. And do you remember what the word delocalized means? Delocalized means that they're shared. There are 6 pi electrons shared between 6 carbon atoms. Shared between 6 carbon atoms. 6 carbons, yeah? Okay, it's called delocalized. So that means when the bromine molecule approaches the pi ring, it does not get polarized. Like it does in an alkene, that does not happen. Yeah? So therefore, it's a little bit more complicated when you react benzene with bromine. Yeah? Okay, so let's have a go at drawing that. So, let's start with the chemical equation then, yeah? The chemical equation. Let's do the chemical equation first. So, when you've got benzene and bromine, yeah? Okay, we need a catalyst to make this reaction happen. Okay, remember that we write catalyst over the arrow, so we're going to use FeBr3. Okay, we don't have to use FeBr3. We could use something like Fe as well. We could use something like that, but for this moment I'm going to talk about FeBr3. Okay, now the mechanism. So the mechanism shows you what happens to the electrons, to the movement of electrons. Okay, to the movement of electrons. So you have, the first step, sorry, take it back. The first step, step number 1, is that you've got the bromine molecule, okay, and it reacts with the catalyst and forms an intermediate. Okay, so then what happens, it generates a positive charge, yeah, and that's your electrophile. Okay, and then the FeBr3 and the Br minus join together, and that's your intermediate. Okay, now because the pi electrons, the pi ring in benzene is delocalized, it can't polarize, yeah, but it can react. It can react with an actual positive charge, yeah, but it can't polarize a neutral molecule. This catalyst, let me just write the name. This catalyst has got a name, yeah. So it's iron bromide, iron 3 bromide, but it's called a halogen carrier. A halogen carrier. Okay, and can you see what it's happening here? Can you see that the FeBr3 is carrying the halogen and just looking after it, the other spare halogen? Okay, right. So we've got our electrophile and we've got the benzene ring. Okay, now we're going to have a curly arrow from the ring. Okay, from the ring like that. So from the pi ring, so we've got the movement of 2 pi electrons are moving out of the ring, okay, to form an intermediate. Now I'm just going to focus on this hydrogen here, okay? I'm just going to focus on that hydrogen there. There is a hydrogen on each of the carbons. There is a hydrogen in every single carbon, but I'm just going to focus on that hydrogen there, okay, the hydrogen at the top. Okay, 2 pi electrons have come out the ring. So what we're going to do now, the ring has broken, and it is a partial ring, okay? Now this is really, be careful when you're drawing this. This partial ring includes every single carbon, but not this carbon here, yeah? That carbon there is joined to the bromine. So the curly arrows formed a covalent bond with the bromine, okay? And this partial ring covers all the other carbons. You've got to make sure when you're drawing this partial ring, you've got to make sure that it doesn't touch the actual carbon skeleton of benzene, okay? Now, we've got a positive charge because it's an electrophile, yeah? 2 pi electrons have moved out of benzene, so here we have got left 4 pi electrons, but the 4 pi electrons are only shared between 5 carbons, so shared by 5 carbons, okay? So can you see there's 1 electron short? 4 pi electrons shared by 5 carbons, so there's 1 electron short. So there's a positive charge in this partial ring. So on the left hand side of the equation, on the left hand side we have a positive charge, we have a positive charge here. You've got to always make sure that the equations, the mechanisms are balanced. Okay, remember that benzene is 6 pi electrons shared between 6 carbons. Yeah, okay. Then we need to reform. So this is just a very temporary thing. We need to reform the benzene ring. So the two electrons from the CH bond come back in and reform the benzene ring. Okay, and then you have your 6 pi electrons now and 6 carbons, and your hydrogen has broken off and it's a H plus. Okay, and this item that we've made is called bromobenzene. Okay, now the mechanism has got 3 steps. Okay, this is step 1, this is step 2, and then we have step 3. Okay, I'm running out of room, so what I'm going to do is I'm going to just write step 3 on the other, I'll squeeze it in, let me squeeze it in up here, step 3. Okay, step 3, I'm just going to squeeze it up here for a moment. Okay, this is step 3, up here. So step 3 is regenerating the catalyst, because FeBr3 is a catalyst. So step 3 is taking the H plus that's been formed, and the FeBr4 minus, and regenerating the catalyst, HBr plus FeBr3. Okay, because remember, catalyst has to be regenerated. Okay, so that's step 3. And that's the mechanism for the halogenation, for the bromination of benzene. Let's go back to the overall equation because we need to finish the overall equation. So we have got benzene. So benzene does react with bromine, but it needs a catalyst, and it will give you the product of bromobenzene. And then the other item was HBr. Okay, and what type of reaction has actually happened here? So again, it is an electrophile because the Br plus is an electrophile, so it's electrophilic, but it's not electrophilic addition. Can you see that the H has been replaced with the Br? Okay, the H has been swapped with the Br, so that is substitution. Okay, electrophilic substitution, will be a tricky word to spell, electrophilic substitution. And also make sure with electrophilic, make sure you've only got one L there. Okay, electrophilic substitution. Now you can do this with chlorine as well, and if you chlorine, your halogen carrier, you could use FeCl3, you could use Fe, you could use AlCl3. Okay, so there are several halogen carriers you could use. Okay, so that's the halogenation of bromine, the first reaction, right? Let's try the next one, the alkylation or acylation of benzene. Yeah, of benzene. Did I say bromine a moment ago? Right. If you take benzene, well, let's see if you can work this one out yourself. Okay. So take your benzene. Right. What are we going to need to add? Okay. And what's the catalyst going to be? All right. In order to make methyl benzene. So in order to make methyl benzene, and then there's another product as well. All right. So just pause the video for a moment and see if you can work out what is needed in order to make methyl benzene. Okay, the mechanism is just the same as the mechanism we've just done just now. Okay, so if you paused it, if you had a go. So you've got benzene. Now can you see that you need a methyl? We need a methyl group. Okay, so we're going to need, the electrophile is going to need to be CH3 plus, because then what happens from the benzene ring, and then you have your intermediate. Oh, benzene's not very good, is it? Oh, no, I don't like that. I don't, because it's nearly touching. So I'm going to draw that a bit more, a bit clearer. Okay, hexagon, and then not touching like that. And then I'm going to put the H. It doesn't matter. Okay, it doesn't matter which carbon on the benzene ring, because this is mono substitution. Okay, the positive charge is within the ring. Okay, don't draw the positive charge. Don't draw it like up there. Okay, you'll lose a mark if you do that. Make sure that the positive charge is within the ring, the partial ring. Okay, and make sure the ring is not touching the carbon skeleton either, which mine nearly was. Okay. Oh gosh, I've done that not very well. Okay, right, then your H comes back in, the 2 electrons from your H come back in, and you reform your ring. You've got methyl benzene and H plus. Okay, so we need CH3 plus. Yeah, so what's this item here going to be then? So we need CH3 plus, so we need CH3 Br. I mean, or it could be Cl, CH3Cl. We need a halogen carrier in order to generate the electrophile, so we're going to use FeBr3, or it can be FeCl3 or AlCl3, and then the other product is going to be HBr. Okay, so this is actually step 2 of the mechanism, which we've shown here. Step 1 would have been first generating the electrophile as step 1, So step 1 is generating the electrophile. So that is CH3 plus FeBr4 minus. Okay, step 2 we've already shown there, and then step 3 is regenerating the catalyst. So you've got FeBr4 minus plus H plus, pardon me, I'm sorry, plus H plus goes to HBr plus FeBr3. Okay, now this reaction is called an alkylation reaction because you're adding an alkyl group, but it's actually more commonly known as a Friedel-Crafts reaction. Friedel, just be careful with your spelling there. Friedel-Crafts reaction. Friedel-Crafts reaction. But you can see that the mechanism is very similar. Okay, right, here's another example for you. Right, you could definitely do this one then, right? So we've got benzene. Okay, what do we need to add? Whoops. What do we need to add? What catalyst do we need to add? What catalyst do we need to add in order to form, I'm going to do a different carbon this time, in order to form this. And what's the other item going to be? Ooh, okay. Alright, pause the video for 2 seconds, have a go at that, yeah? Have a go at that, see if you can work that out. Right, so this is the electrophile, yeah? So what we're going to need is we're going to need benzene, and we're going to need C double bond O, CH3, and then we're going to need that to be a positive charge. I'm going to lose that because it's a bit confusing. Right, and then the mechanism is just the same, pair of electrons from the benzene ring. Okay, move out, then you get your intermediate. So let's draw the intermediate. I'm going to do it off this carbon, doing it off a different carbon, like that. So now it looks a little bit weird because the partial ring is going to be all the carbons, but not that carbon, yeah? But all the other carbons, 5 carbons. Then we're going to regenerate the ring, pair of electrons come back in, and we get the we get that, there we go, plus H plus. Okay, so that's, remember that that's step 2. Okay, so we've not actually shown step 1 yet. So step 1 of the mechanism will be to generate this electrophile. So you're going to need your FeBr3 or AlCl3 or something like that, and then you're going to need your actually, it might be easier, why don't we actually this time, just to put a bit of variety in there, why don't we actually use AlCl3? Okay, and then can you see what functional group you've got here? Yeah, so this is one of the functional groups you need to know about, acyl chloride or acid chloride, you might know it as well. Yeah, and then you're going to generate your electrophile, C double bond O, running out of room again, need to write smaller. Okay, and then the third step is to regenerate the catalyst. Okay, so that's where you've got AlCl4 minus plus H plus, and that will give you AlCl3 plus HCl. So your other item is going to be HCl up here, plus HCl, just put a bit of variety in there. We're going to use AlCl3 as the halogen carrier, and the other reagent is going to be acyl chloride, ethanoyl chloride. Okay, and this is called acylation, also Also Friedel-Crafts reaction as well, acylation, and that's a Friedel-Crafts reaction as well. Okay, so Friedel-Crafts is about making a carbon-carbon bond. So carbon-carbon bond, and on the previous example, we're making a carbon-carbon bond. Okay, the last reaction is the nitration of benzene. Okay, so the nitration of benzene. And this is one of the most popular reactions when you're talking about the reaction of benzene, nitration of benzene. So we'll do the chemical equation first, the balanced chemical equation. You take your benzene, you take nitric acid. It is supposed to be concentrated nitric acid. Okay, you've got a catalyst, which is sulfuric acid, and again it is concentrated, okay, and the temperature is 50 degrees. Okay, so we're putting these conditions over the arrow, right? So, and then you have got then you have got your product, which is nitrobenzene. Again, it doesn't matter which carbon we put it on. That's nitrobenzene. I'm going to write its name up here. Nitro. This is a that's a nitro group. Nitrobenzene. Benzene. Okay. And then plus. What's the other item going to be? Can you work out what the other item's going to be? It's water. Yeah, good stuff. Alright, so water. So the mechanism. So the mechanism comes in 3 steps, just like all the other mechanisms. Okay, so this is the mechanism. So step 1, right, is when you generate the electrophile. So you generate the electrophile with nitric acid, concentrated, plus sulfuric acid, concentrated, and this makes something called NO2+, okay, and that's a nitronium ion. It might go by, it does go by different names, plus HSO4-, plus the other item is water. Can you check it's balanced? Always check your equations are balanced. Okay, step 2 is the actual reaction with benzene. So now we've got the electrophile, which is NO2+. I'm sure you can do this mechanism quicker than me now. Yeah, pair of pi electrons. 2 pi electrons come out. You form an intermediate. Okay, I'm going to choose this carbon. Doesn't matter which carbon you choose. Okay, but make sure your partial ring is all the other 5 carbons and a positive charge. Regenerate the benzene ring. Then you have your nitrobenzene plus H+, and then can you guess what step 3 in the mechanism is? Step 3 in the mechanism is when you take you regenerate the catalyst. So look what you've got here. You've got HSO4-, so HSO4- plus H+, and that regenerates the catalyst. Okay, so and there's just one more thing. Oh, this is electrophilic substitution, because the electrophile is NO2+. Yeah, so when you're actually doing this in the lab, you've got to be careful of multiple substitution. Okay, when you're actually practically doing this, you've got to be careful of multiple substitution. So for example, right, so for example, you've got methylbenzene. Yeah, if you substitute methylbenzene, you have got that. Okay, and methylbenzene used to be called in the old days toluene. Okay, and so this is called trinitrotoluene. Trinitrotoluene, TNT, which is an explosive, and therefore in the lab we don't do 50 degrees. We actually practically do below 10 degrees in order to prevent multiple substitution. We do practically we do below, but for exam questions you have to say 50 degrees.